Hello, and now we get to the fun stuff. Relativity and quantum mechanics, beginning with chapter 37 of Young and Freedman's University Physics. We begin relativity. And while you were off on a spaceship, almost going the speed of light, I've aged considerably. It's called the grandfather paradox, but wait for that. It'll be coming in a video not too long from now, maybe. But we want to begin chapter 37 on relativity. Relativity is, of course, associated with the name Albert Einstein. Albert Einstein, in 1905, published 3 papers. He actually didn't win the Nobel Prize for the paper on special relativity, but he actually won the Nobel Prize for his work on the photoelectric effect, as it's called. But that's yet to come in these videos on chapter 37 and beyond in Young and Freedman's University Physics. But we begin today with the first section of chapter 37 on relativity, the invariance of physical laws. What does invariance mean? It's not a word I use very often. In fact, I don't think I've ever used it. May have never even said it. I don't know. It means it doesn't change. Invariance means physical laws don't change. Einstein has kind of, we talk about his special theory of relativity and his general theory of relativity. His special theory of relativity has to do with the fact that there's some contradictions that 1800s physics had left at the end of the century. And Einstein, who was just a patent clerk at the time, now don't let that fool you, he was a very smart patent clerk, but he wrestled with these privately. And then in 1905, he published his paper, in which basically he argues that space and time do not appear uniform, that in a sense, space and time appear to move at different rates depending on where you are looking at them. I'm getting ahead of myself. But the special theory of relativity has to do with that. The general theory of relativity, which came out in 1915, 10 years later, after great struggle, and he needed a little help with the math from David Hilbert. In fact, there's a debate about whether actually Hilbert was the one to first come up with the understanding of the theory, but Hilbert deferred to Einstein, and I'm glad he did, although I'm not sure whether Einstein, clearly if there was no Einstein, there would be no general theory of relativity. But I'm not sure that he would have been able to bring it out if there hadn't been a David Hilbert. General theory of relativity has to do with large masses, like, what happens to space and time around the sun and things like that. Well, obviously, I find this a very interesting subject, and I'm getting out of business. The business of today is the first section of chapter 37 of Young and Freedman's University Physics, the unchangingness of physical laws. So there are 2 postulates that stand at the root of Einstein's special theory of relativity. So the first one is that the laws of physics are the same in every inertial frame of reference. This doesn't seem that controversial to us. It basically says that no matter where you are, whether you're on a spaceship or whether you're on the Earth or whether you're standing out in the middle of space for no apparent reason, or you're in Alpha Centauri, or wherever you are in the universe, the laws of physics work exactly the same. Now, this expression, inertial frame of reference, basically means has to do with a kind of situation you're in. So let's say you're on a spaceship, then you're on an inertial frame of reference. Let's say you're on the Earth, then you're on an inertial frame of reference. And so one is moving at a particular rate in relation to another. So we find ourselves on various inertial frames of reference in our life. If you're on a train, I don't know if you've ever been on a train. I've been to, I spent a little time in England and Germany and Europe in my younger days. And if let's say you're sitting on a train that's about to depart, but there's a train right next to you. Well, sometimes if the train next to you start moving and you look over, you're not sure, for just a few moments, you're not sure whether you're moving or whether the other train is moving. when you're on a plane, I've been on a number of planes recently, and so when you're going, you may be going 400 miles an hour in the plane, but you don't feel like you're moving. You're on an inertial frame of reference. Inertia, of course, is a body in motion wants to stay in motion, for example. And so you're on that frame of reference. Now, you can have accelerating frames of reference, but so think of a frame of reference as a context that you're in. And it's in an inertial context. That is, that everything in that context is moving at the same rate or accelerating at the same rate. Everything in that context is a package deal with regard to motion. And so there's the train inertial frame of reference. Everybody on the train is in that group of motion. Everybody on the plane is on that frame of motion. Everybody on this where I'm at on the earth is at this frame of motion. And you don't even know you're moving. I mean, I'm on the earth right now, and I think I'm still, but I'm not. I'm moving very fast right now. It's just that I'm in an inertial frame of reference, and I don't really know it. Of course, it's spinning, which messes everything up. But I'm going to try to stop my mouth from talking and move on to the other postulate, which is, and this is the problem. This was the problem. Maxwell's equations, which if you've gone through Young and Freedman in order, you've already covered Maxwell's equations. Maxwell's equations had to do with electromagnetism and Faraday's law, all those sorts of things. And Maxwell's equations suggest that the speed of light is a kind of constant, especially say in a vacuum. That in a vacuum where there's no air or anything like that, that the speed of light seems to be a kind of constant. Now, this is where Einstein took this seriously. Einstein said, what happens if the speed of light in a vacuum is the same in all inertial frames of reference? And that it doesn't matter whether the train is moving or the plane is moving or the earth is moving or you're standing still with a flashlight in the middle of outer space, that no matter where the light comes from, it is going to move at the same speed. 3 times 10 to the 8th power meters per second, roughly. If that's the case, it messes up space and time. It messes up space and time because in order for that to be true, then the space that the light is covering has to be smaller, or the time that the light is covering has to be slower. This is what messed Einstein up, and he decided that he was just going to go with it. That rather than, at the time, people were saying, well, there's this mysterious thing called the ether. It's all around us. The ether is all around us. And that the ether actually changes the motion of the light depending on the inertial frame. That was the prevailing theory at the time. But Einstein said, what if there is no ether? What would be the implication of following these two fundamental ideas through? Okay, hold that thought. We'll come back to it later. So basically, Einstein followed the kind of where Maxwell's equations seem to be leading him, with the conclusion that it is impossible. Oh, I'm sorry. So basically, that everything is going at the speed of light. Now, one of the first implications of this is that no one can travel at the speed of light. That it's impossible for me or any observer on any inertial frame, it is impossible to travel at the speed of light, at c, which we call c. You've heard E equals mc squared. Well, the c is the speed of light. It's impossible. Why? Because the light always has to emanate from wherever you're at. So if you're on a spaceship going the speed of light and you shined the headlights on, light wouldn't go anywhere. And so the light has to go somewhere. And so therefore, nothing can go the speed of light. So this is one of the consequences of Einstein's postulates, that there is an ultimate speed limit to the universe. That speed limit is c, 3 times 10 to the 8th meters per second squared, and nothing but light can travel at that speed. So that's the first consequence of his postulates. So previously it was suggested, I already said this, that there was a universal ether that would make the speed of light appear different in different directions. But the problem is there had been an experiment just a few years before Einstein, the Michelson-Morley experiment, that basically showed this wasn't true. Michelson-Morley tried to detect variations in the speed of light depending on you know, whether you were going in the opposite direction the Earth was spinning or the same direction as the Earth was spinning. And what the Michelson-Morley experiment concluded was there ain't no difference. The speed of light is the speed of light, and it doesn't matter where it's coming from. The speed of light is always going to be 3 times 10 to the 8 meters per second. And therefore, the ether was toast. Toasted ether. Try it. Now showing at a McDonald's near you. Okay, so the Michelson-Morley experiment disproved this idea. So Einstein went with it. Okay, more on Einstein in videos yet to come. Let's go back. Let's step back a bit and go back to Galileo Figaro. Galileo. Galileo lived in the late 1500s, early 1600s. And so Galilean transformations has to do with Galileo. You know, I'm a Christian, so at first I thought, Galilee, the Sea of Galilee? But this doesn't quite go back to Jesus. The Galilean transformations go back to Galileo in the late 1500s, early 1600s. Now what we have here is we have 2 inertial frames of reference. We have inertial frame S and inertial frame S prime. And it's fairly standard because of my pea brain and others, the pea brains of others, to align the inertial frame. So let's say there are 2 inertial frames. Let's, for the sake of simplicity, let's just say that inertial frame S is not moving. Okay, so inertial frame S is stationary out in outer space somewhere. It's not moving, just there, no motion. And O is the origin. There's the y-axis. Here's the x-axis. Okay, so it's just nice. Just kind of block in your mind this axis here, and you've got frame S. It's a frame of reference in motion. Now let's say, again, for pea brains like me, that the x-axis coincides with the x prime axis of the other frame, and that frame S prime is moving to the right at a uniform velocity in a way that is the only difference is that the x is changing. So the y is completely parallel. The z is completely parallel. The only thing that is altering, so y equals y prime at every point, and z equals z prime at every point. But what is changing is the x prime. X prime is moving in this direction. Okay, so we've got them completely aligned, but one is moving. Okay, and we're doing that for pea brains like me. Let's say u is the velocity of frame S prime relativity. U is the velocity of S prime relative to S, and that at t equals 0, t prime equals 0, that the origins coincided. So at t equals 0, S and S prime were exactly overlapping each other. And now in Newtonian physics, Newton lived in the 1600s. In Newtonian physics, we would assume that t equals t prime. That is, that time in frame S is going to be exactly the same as time in frame S prime. This is where Einstein is going to say, maybe not. But anyway, that's, again, future videos. So what Galileo said, if we want to know what x is, that is what the distance of a, let's say we've got a point somewhere on frame S prime. Let's say somewhere out here there's a point P on frame S prime. If we want to know where, so we know where it is on x prime. So on x prime, let's say it's moving at a uniform velocity, then point P is always going to be at the same point on x prime, right? Just like on the train. The train is moving, but I'm not changing seats. I'm in the same seat on the train. The train is moving, but Ken's in the same place on the train. Mind blown. No, I mean, we all know this, right? You get on a plane, you sit down, and you're stuck, you know, for however many hours, unless you can get the people next to you to get up so you can use the bathroom. But that's not important right now. I mean, when you're on a moving frame, you know, the frame may be moving, but you're in the same spot, right? And so let's say you have a point P in frame S prime. It's somewhere out here on x prime. It's going to be in the same place all the time, even though S prime is moving. But here's the question: where is it at any point in relation to S? Well, it's not a hard proposition, because we know that it's at a certain point on x prime, right? And so basically all we need to do is add however much distance. Remember at t0 they coincided, but now as prime has moved on, all we need to do is figure out how much distance has passed as the frame is moved. And the way to do that is fairly easy. We're going back to the beginning of physics, beginning of our pilgrimage, way back in what was it, chapter 2, chapter 3, long time ago. But basically, velocity times time gives you distance, right? If you're moving at 5 meters per second, you know, and you wait 5 seconds, then you've gone 25 meters, right? Velocity distance equals velocity times time. And so we know that the frame has moved. Velocity, u is the velocity of frame s prime, times time is going to give you the distance that it has traveled, that is the distance that frame s prime has traveled along this x-axis. And if you add that distance plus the distance that the point is on x prime, ta-da, you've got x. Very simple. Okay, so x, wherever the point is on frame s, is equal to x prime, wherever the point is on x prime, plus the distance the frame has traveled, which is the velocity of the frame times the time it's been moving. So there you have it. X equals x prime plus ut. Galileo came up with this way back, you know, around 1600. Okay, so these are the transformation equations. Where x equals x prime plus ut, but we've said that y equals y. We're not varying those because our brains are pea brains. Okay, nice. Okay, we're almost done with this video. So now we have calculus. We know calculus, right? We're smart people. Let's go ahead and take the derivative of this equation. So dx dt, the instantaneous change in distance per time equals the instantaneous change in distance in x prime per time plus the derivative of this. Well, the derivative of ut is going to take when you take the derivative of something like ut with respect to t, the t goes down 1 power. Right now, it's t to the 1 power. And so when I take the derivative of it, I multiply the 1 by u, and then I take it down a power, and it becomes t to the 0. Well, anything to the 0 power is 1, and so the t goes away, and I'm left with just u. So this is a logical consequence of this. Well, I can express this in another way, right? This is simply velocity of something in frame s. And then this is velocity of something in frame s prime. And then I'm left with the u. And so here we have the transformation, the Galilean velocity transformation equation. Okay, now, final thought for this video. Let's go ahead and plug in the speed of light to this. So the speed of light in frame s would then equal the speed of light in frame s prime plus the velocity of the frame. In other words, c would equal, now this makes sense if you're throwing a rock. If I'm on a train, going v prime, I'm sorry, the train is going u, then the velocity of a rock I throw from the top of the train, because I'm in a movie, the velocity of that rock in relation to the ground is going to equal the velocity of the rock plus the velocity of the train. That makes sense. But if the speed of light is always the speed of light, this doesn't work. Because then the speed of light would be faster than the speed of light. Does not compute, does not compute. Speed of light is just the speed of light. It doesn't change. And so we find that the Galilean transformation equations don't work with regard to the speed of light. In fact, what we're going to find is they just don't work when anything's velocity begins to approach the speed of light. And that was the little speck, the little piece of dirt in the clam that brought the pearl, in the oyster that brought the pearl. Okay, forget the illustration. Basically, this was the seed that brought Einstein to the special theory of relativity. Well, I hope I've used too many words in this video, but I've enjoyed it, and I hope you've enjoyed it too. And we will be back with next video, the relativity, the relativity of simultaneity. There's a word. Okay, We'll see you next video on relativity.